Welcome everybody to Crash Course Electronics and PCB Design. This is another bonus lecture. So every month, for those of you that are new students, we're going to have a bonus lecture, usually on something electronic based, right? It's an electronics class. However, it could be on software or firmware or something more advanced or less advanced. It might even be on something mechanical or 3D printing, gaming or retro related. It's just kind of dealer's choice, whatever I kind of feel like would be cool to talk about. So this month, I had a project all set up that I was going to do, which now I can't remember. However, I was talking to a friend of mine, and he was talking about solderless breadboard power supplies. So these are these power supplies that you can plug into a solderless breadboard. So we've got, one of these right here, solderless breadboard, and a lot of you may even actually have one of these. You can plug them in to the breadboard and power it off USB or something else, a wall wart or a wall adapter, and then you kind of have a 5 volt, maybe a 3.3 volt power supply. So you can get these things on Amazon or eBay or Banggood or whatever or wherever you shop at. However, there's a pervasive problem with all of these products, at least the great majority of them. And that problem is they don't work. They are broken. They are poorly designed and do not do what they're supposed to do. So in this lecture, not only are we going to design what you see on the screen right here, which is a power supply, a solderless breadboard power supply. We're going to design this. Now we're not going to go lay this whole thing out because it would take hours and hours, but we're going to look at the schematic, we're going to go through all the parts, and we're going to go through the thought process I had as I laid this out. And of course you're going to learn to do all this in section 8 of the course as you go through PCB design. So if you haven't gone through any of the course and you're just skipping and looking at a bonus lecture, you're still going to get a lot out of this. All right, so just follow along. All right, so anyway, what we're going to do is we're going to kind of go through taking a look at some of these other products. We're going to go on the bench, and I'm going to prove to you that USB ports do something that these power supplies do not compensate for. And then we're going to come back and we're going to work on this PCB. We're going to look at the schematic, we're going to look at the layout, then we're going to get it ready for manufacturing, and we're going to go manufacture it. All right, so that is the plan. All right, so let's start. Let's see here. Before we start, a couple things. So everyone knows I'm a game developer, a gamer, a retro gamer. I build game consoles. I used to write video games, so it's a big part of my interests. And even though I'm not currently developing video games, I still am very interested in it, and I always get the itch to make one. Anyway, I like to keep up my reading with different things, and so a couple things just came out, which is kind of cool. So this right here, if you can see this, yeah. So this is the Stella Programmer's Guide, and Stella was the chip inside of the Atari 2600. So this is a very, very cool book. So this is, I think this was written in like 1979 was the original date. Yeah, 1979. So this was by Steve Wright, and this, I read this back in 1979, if you can believe that. And yeah, it's only like 50 pages or so. Yeah, it's like literally 50 pages long is the end of the book, 50 pages. But this was all we had to kind of program the Atari 2600. It was very hard to get your hands on. Anyway, it's been kind of reconstructed and cleaned up, and you can get that online if you just I think it's on Amazon. I think that's where I got it. So anyway, the Stella Programmer's Guide, if you're a retro game fan and kind of want to understand how the Atari 2600 worked, which is a really interesting model of hardware, I highly recommend that book. It's like, the classic book, 1979, long time ago, right? And then, so there's another student, I'm sure there's many students in this course that are into retro game development and hardware and so forth. And one of the students, his name is Derek Morris, and he just wrote this book, and I thought I would put it up here. So this is his new book here, all right? And it's just called Retro Game Dev by Derek Morris, and it's about the Commodore 64, which is an awesome 8-bit computer from the 80s. And depending on who you listen to, it was the best-selling computer of all time, and it sold, I don't know, somewhere, depending on, again, where you get your information, it's 15 to 20 million units, crazy number of units. Anyway, the Commodore is a great machine to do graphics on. It has sprites and you can do tile graphics, you can do bitmap graphics. It has a very advanced sound processor for the time. Anyway, this book, which you can kind of go online and find on Amazon, or you can get it in other places, Retro Game Dev by Derek Morse, it takes you through and kind of teaches you a little bit of 6502 assembly language and kind of how to get sprites on the screen, and he makes a couple games in here, a space game and a platformer. So very cool. It's a pretty short read. It's about I think it's 120 pages maybe. Yeah, about 120 pages. So you can read it in a night. I read it in one night, and I was very happy with it. It's very, very well done. So check out that book if you're interested in that. So those are a couple things. That's why I said these lectures, we're going to kind of be all over the place with them. Was there anything else I wanted to show you guys? There was one other thing. So I've been working on a new game console, which I can't say what it is. But anyway, so here's the first PCB of it. And so this is much larger than it. It's very small, but this is kind of how I evaluate it. So I'll put this together and check it out and see if it works. And then if it does, then I'll continue shrinking it. So anyway, so that's kind of cool. All right, so let's go to Amazon here, and let's see what I am talking about. So if you type into Amazon, solderless breadboard power supply. So a lot of you are on a budget, and a desktop power supply or a bench power supply, can cost anywhere from $50 to $5,000. So my power supplies are a couple $100, $150, and then that one's about $300. And then I've got another one over here, a Rigel, which is about $800 or $900. So they're not cheap. And that's because they have to be very low noise, very precise. They have to be able to regulate the line, regulate the load, and be noiseless, all those kinds of things, right? And again, during the class, you'll learn a lot about this because we do power supply stuff inside of the course. But anyway, if you just want to get a power supply to kind of plug into your solderless breadboard to make some of the projects, even in this class, and you just want your 5 volt and 3.3 volt supply, then you can get these little products, which are pretty cool, but there's a big problem with all of them. So if we scroll down here, we see there's kind of this product here, there's this other product here, and there's different variants. So let's take a look here. We'll take a look at this one right here, JBEC, and they're all the same thing, right? So you take a look at this product right here, all right, and you can see it kind of plugs in on the solderless breadboard there and there, right? And then there's a jumper, and the jumper basically, so there's two regulators on here. One's a 3.3 and one's a 5 volt regulator. And then on each one of these rails, you can either pull the jumper off and not have any voltage, or you can move the jumper and select either 5 volts or 3.3. So it allows you to put 3.3 and 5 on either rail or nothing. All right, so that's cool. Then there's an on and off switch. Then it takes, this particular version takes a USB connector. All right, and then it also takes a 2.1 millimeter wall adapter power supply, and then it's got a little green LED. All right, so we're going to get into why this is such a bad design, but just starting off, we can see we've got these two regulators. These are linear regulators, right? And again, if you don't know anything about electronics yet, so there's two different classes of these regulators. So one is called a linear regulator, and basically the linear regulator, if you put in a higher voltage and you want a lower voltage out, it basically burns that voltage through resistance. So it controls a feedback loop, and it basically applies a larger, smaller resistor, and then it reduces that voltage so that on the output of the regulator, you get your desired voltage, and no matter what's happening to the input, it will maintain that. Also, no matter what happens to the load, as you increase or decrease the load, the voltage will stay the same. Linear regulators are fine, but they're very inefficient, and they burn a lot of energy, and they get very hot. There's also another problem with a linear regulator. If you're trying to regulate a voltage, let's say you want 5 volts, typically you need a voltage higher than the 5 volts as the input. And depending on the quality of the regulator, like if it's old 7805, you may need a couple volts. So if you want to regulate 5 volts, you need 7 volts always or higher to maintain the regulation. Now, we have what are called modern LDO or low dropout regulators, and these regulators require anywhere from 0.2, 0.3, or 0.4, maybe 0.5 volts and higher, but the whole idea is they require a lower voltage over the regulated voltage. So say if you're trying to regulate to 5, you could probably find a an LDO regulator that could maintain that 5-volt regulation even with an input that would drop down to say as low as 5.2 or 5.3 volts, but it still has to be higher, and it has to be higher by a large enough margin so the electronics can work in there. Okay, so we'll circle back, but there's a big problem because these linear regulators on here, these 117 AMS 1117. There's a 5.0. You can see the 5.0 and you can see the 3.3. Let me see. Can I click this? Yeah. And 5.0 and 3.3. So we can look this up and we can look the specs up of this. All right, and we will. All right. So let's go back. All right. So that was one. There's another one, and there was another. There's another like smaller one. Let me see if here we go. So here's another one. And you can see they all kind of follow the same thing. And then this is a common theme. What happens is someone sees an idea and they copy the idea and they just keep copying the bad idea over and over and over. And this happens a lot. So you can look, it's still got that same exact chip, AMS 1117, AMS 1117, 3.3, 5.0 volts. It's almost an identical design. It's got a couple switches this time, which is cool. All right. And then this time it's got a a mini USB connector, so mini B USB connector, and it's got a couple capacitors on there, LED. Things are moved around a little bit, and then this component here, this looks like a fuse, a polyfuse, but it's the same design again. All right, exactly the same, and it's not compensating for the problem I'm going to tell you about. All right, and let's see, is there anything else? That one. And looking around, and of course there's hundreds of these. You can just go online and find all kinds of crazy variations of them. All right. So anyway, what I did was I looked through all of these and I looked at some of the design elements they had, and then said, let's build a better one within reason, within time and space here, because we don't have, forever. We've already used up like 12 minutes or whatever of video just talking, kind of explain. All right. So what I want to do now is let's talk about the design of something like this. So we know we want this to plug into a solderless breadboard. So we have a number of things that we need to consider, right? And one of those things is how big is a solderless breadboard? So we're going to go over to the bench at some point and we're going to start mucking around and measuring stuff. So we got to worry about how big is the solderless breadboard. For example, this thing has got to kind of plug into these two areas right here and then kind of wrap around this, right? So the question is, what's the distance between there? Interestingly, it's not standardized. So what is standardized is the middle here, in the middle, from one side to the other, this is 0.3 inches always, because ICs, standard DIP packages, dual inline package, they have 0.3 inches between them. So this is 0.3. So one hole from the top to the bottom is 0.3. We know that. But from here to here, there's no real standard, so it varies. All right. Anyway, so I had to measure this with calipers under a microscope because I literally couldn't find this. And I figured out it's about, I think it's 42 millimeters from the two inner rails and then 47 to the outer rails. But we know that if you can measure one rail to one rail, the other rail is 0.1 inch. So one thing is true, it's always 0.1 inch between these rails. So anyway, we need to make that line up. All right, so that's important. Okay, now, the big problem that we said about these kinds of power supplies is that they're based on two different kinds of inputs. All right, so let's go back real quick here and let's pop one back on the screen. This one. All right, so we can get the input from this adapter, this DC adapter in. Now, if we do that, depending on their design, and we're assuming that they're doing what I'm saying they're doing, and they are, let's click this. What's happening is this DC supply is coming in here, which could be very high voltage. It could be 9 to 12 volts DC or 6 to 12 volts, someplace in there, right? And that higher voltage is then going to go into each one of these linear regulators. Now, if it's a really poor design, what they're going to do is they're going to put the DC voltage into the 5-volt regulator first. They may regulate it down and then put that into the 3.3 volt regulator and then regulate that down. That is a big, big, big no-no. Typically, you don't want to do that. The reason you don't want to do that is because say the 5 volt can support 500 milliamps, right? Okay, so it can support 500 milliamps of current. You take its output, then you feed it into the 3.3. Let's say it can support 500 milliamps of current, right? Well, wait a minute. The 5.0 is feeding the 3.3. So let's say the 3.3 wants to pull 400 milliamps. Well, that leaves the 5.0 with only 100 milliamps left to supply other 5 volt devices. So that 3.3 is kind of artificially sucking away current from it. You don't want to do that. So what you want to do is when you have a DC input, you want to separately send it to all of your different regulators, unless one of your regulators is a very small regulator and it's not using a lot of current. So in other words, if we kind of go here real quick on our drawing program, and we go here and say here's our DC, and then let's say this is 6 to 12 volts, right? All right, so there's our DC line, right? And say this is plus, and then we've got a and we're just going to do this as a block diagram here. Let's say that this is a 5 volt regulator here, all right? So then we're going to get this nice 5 volts out, right? And then let's say that we have this 3.3 regulator here, right? And then out of here we're going to get this nice 3.3 volts. Okay, what we don't want to do is this. We don't want to take this and put this into here. All right, you could, there's nothing wrong with it, but you siphon current away from the 5 volt. So now the 5 volt going to other devices is going to have a reduced current output. Bad, bad, bad. So what we want to do is let's put that V back on there. What we want to do is take this and go like that, just in parallel. And then if you had more regulators down here, more regulators, say another regulator for 1.8 volts or something like that, again, we just go like that. All right, and we just do all these in parallel. Okay, that's that's how we want to do this. And then additionally, if we have them all in parallel, say if the 5 volt got noisy for some reason, right? Well, if the 5 volt was over here feeding the 3.3 and then the 3.3 was over here feeding the 1.8, well, that noise is going to then go here, and then it's going to go here, and then it's going to go here, and then it's going to go here. You're going to have noise everywhere, right? But if these things are all separate, right? If they're separate, if there's noise there, then the 3.3 doesn't notice it, the 1.8 doesn't notice it, and so forth. So that's how we want to design these power supplies, okay? All right, so let's go back here. Okay, so now what I want to do is I want to go on to the bench, and we are going to quickly, I'm going to prove to you a problem. And the problem is this. So if we have the wall adapter powering this with 6 to 12 volts, that will be enough voltage to maintain the 5 volt supply. The 5 volt is the problem. The 3.3 volt, if we have 5 volts or 4 volts, it'll probably be okay. It'll maintain regulation depending on these regulators, this AMS 1117, which we're going to look up in a second. But the 5 volt is going to be a problem. Let me tell you why it's a problem. If you look up the USB specification, the USB port specification is something like the voltage has to be 4.7 to 5.2 volts, and this and that and so forth. No one follows it, maintains it, whatever. So a lot of these USB ports could be 4.7, they could be 5.1, they could be 4.8, they could be this and that all over the place. That's if they are, say, a computer port, right? Then they could be on a powered hub, or they could just be a charger, right? A USB charger. All of these are supposed to be dead on like 5 volts, but a lot of times they're higher than 5 volts. And the reason why they're higher than 5 volts is because a lot of times you have to go over a cable, and that cable is going to have a big voltage drop over it, 0.2, 0.3, 0.4 volts. You'd be surprised what a cable drops when you're dragging an amp of current or 2 amps of current through it for, say, a pad that you're charging, an iPad or an Android pad. A lot of current gets sucked through there. So they compensate by making the voltage higher. And then typically these are going into charging systems. But the voltage is not regulated. It's going to be all over the place. So depending on what the load does, right, that voltage, that 5 volts, is going to keep dropping and dropping and dropping. So here's the problem. If this regulator, this 5 volt regulator, requires, say, 1 volt above 5 volts to maintain regulation, well, already that's not going to work because the USB input, maybe if we're lucky, is 5.1 volts. So there's no way it can regulate because it would need to be 6 volts for that regulator to regulate. So the problem is that the moment we plug anything into this, the regulator basically is not going to be used. It's not going to regulate anything. So as we connect our electronics up to the 5 volt supply, When this is in USB mode, when a USB cable is plugged in, either a power supply or a powered hub or a computer, that voltage is going to be less than 5 volts when we apply loads to it, and it's not going to be regulated at all. So you have a completely unregulated power supply for the 5 volt. Every single one of these has this problem. So how do we fix this? Well, we fix this with a proper power supply. We put what's called a boost converter, which is a switching power supply, on that 5 volt line, so that as that 5 volts goes down or goes up, right, we can put what's called a boost buck converter, so it can compensate if the voltage goes lower or goes higher. No matter what the input is, the output will always stay at 5 volts. So as the input goes like this, the output will stay at 5 volts, and that's what we want. So that's what our system's going to have. But I want to show this to you because a lot of engineers make this mistake. A lot of I know engineers that have been doing it 20, 30 years. They make the assumption that the USB is a regulated 5 volt supply, and it is not, right? And then if you try and use that in a digital system, maybe you're getting 4.7 out, maybe you're getting 4.9, maybe you're getting 4.6 as the load in your system changes. But one thing is for certain, if you have a regulator like this little solderless breadboard, it is not regulating. That chip, you might as well take that 5 volt out because it is not doing anything. That 5 volt regulator, that AMS 1117 in this particular case. Okay. So I want you to meet me over at the bench, and we're going to do some quick experiments, and I'm going to prove this to you and show this to you. All right, so I'll see you over there. Okay, so we're over here on the bench, and oh yeah, this is from Jiu-Jitsu, so that's a mat burn, so excuse that, sorry. So anyway, we're over here on the bench, and we've got a solderless breadboard here. We've got another one here, for example. You can see they're almost identical. All right, so the one thing that I had to do, like I said, was take a pair of calipers, right? These are called calipers, and they work in, these particular ones are millimeter or inch, all right? And then you basically measure, so if you put it in millimeter mode, and then we sit here and we measure this, right? And we want to go to the outside, say the outside to the outside, and make it exactly, and of course I did this under a microscope before, so you know it's roughly 47 millimeters, right? And then we know that from this point to this point is 0.1, and from here to here is 0.1 on the other side, right? So that's how you can kind of figure this out. So when we're doing our mechanical design, we're going to kind of do this kind of thing, this kind of thing, this kind of thing, this kind of thing. That's where I got those numbers from, all right? Okay, so what I want to do, let's zoom in a little bit so we can see what we're doing here. And this is going to be super cool, all right? So this is going to be cool. All right, so I've got this little board here. Let's forget about that for a second. And what I want to show you is I've just got 3 random power supplies here. Here's an HTC. This, of course, is an Apple. This is a real Apple power supply. This is a 1 amp. Now, if you look on here, what's interesting, all right, and of course, they write this totally small, absolutely miniaturized writing. This one's supposed to be 5 volts at 1 amp. 5 volts at 1 amp. All right, fine. This one is supposed to be 5 volts at 1.5 amps. Okay. And this one I already know is 5 volts at 2 amps. This one's a 10 watt. All right. So that's what they say. Okay, so that we have that kind of thing. All right, so we're going to kind of test a couple of these, or maybe we'll try and do all 3 if I can go fast here. And we're always up against time because I have to do this in one lecture. Now here's another little device that I suggest everybody have. These are like $5 on Amazon, and this is basically an inline power monitor. So it measures the voltage on the USB port and the current flowing. This is very, very helpful. So the second that you power this up, this display will turn on. You can kind of tell what's going on, right? So this is a very useful device. These are like $5. And this particular one is called Power Jive. Power Jive. Cool. All right. So what are we going to do? What we're going to do is we're going to create a test circuit, and to create a test circuit we are going to need a USB cable. So we're going to need a USB cable, which is right there, and we are going to then create a cable, and in the course I create many cables, and I show you how to do this. But basically, you know, this has been cut open and then been soldered on here, and then this is shrink tubing so I can see everything, and I've exposed +5 and ground. So typical standard USB cable has 5 volts ground, which is called V-bus is the 5 volts ground, and then it has data plus, data minus, and it also has a couple other pins depending on the version. There's an ID pin, but all we care about is +5 and ground. All right, so we need a way to contact this so we can measure this voltage, right? So then that's what that connector is for. Then I've got this little right angle connector right there. So I'm just going to put this in here carefully, always carefully. Everything is careful. All right, so keep that right there. All right, then I'm going to just kind of safely wrap this cable here. Now what I'm going to do is I'm going to go plug this cable in to, let's take the little Apple one. All right, so now we're doing, you know, basically chargers. All right, just USB dumb chargers, not even a PC port. Okay, now we're going to get our meter. All right, so here's the meter. And then what I'm going to do is, as usual, I'm always fighting to try and fit things on the screen here. Oh, that's not bad. Okay, so we'll put that right there. Now we're going to put this meter into voltage mode. All right, good enough. And there are the probe leads. And now what I'm going to do is I'm going to connect this over here. All right, so this is going to allow us to measure the voltage. So basically we've got the +5 and ground, and now I'm measuring the voltage. So this is the no load voltage. There's no load on here, right? And here's the 5 volts from the USB. And so what we're going to do is we're going to put a load here, all right? We're going to put something on there that's going to drop the voltage, and we're going to drive some current through it. And the question is, how is this voltage going to change? So right now it's 5 volts, all right? And remember, we're going over this cable. This 3-foot cable, all right? So there's going to be a voltage drop over the cable, all right? So I'm going to grab some resistors here. Okay, so right now we've got 5 volts here. So my problem is that if we were to put this into a linear regulator, I guarantee that linear regulator can't regulate this, okay? So at best, it would pass this, and we would get this 5 volts out. So we basically, we're using one of the Solderless Breadboard power supplies. We hook it into our system, and the regulator on there is not doing anything, so we're going to get this voltage out of there. Okay, fine. So we put, say, a 1K resistor, okay, brown, black, red. All right, and we put that on there. All right, and then we're going to get a little current through there. How much current are we going to get? V equals I times R, right? V equals I times R. Okay, so I equals V over R, right? So what do we got? We got 5 divided by 1,000, all right? And so that equals, right, 5 milliamps, right? 5 milliamps. Okay, so that's 5 milliamps. 5 milliamps, nothing's happening. Okay, that 5.07, you know, went back up to 5.08. Okay, let's get a little more brutal. Here is a brown, black, brown. So what's that? That's 100 ohms. So that's going to be 10 times more current, right? So that's going to be 50 milliamps. Now look at that. We dropped to 5.02. Still tolerable. I'm okay with that. I'm okay, right? But our regulator is definitely not regulating on that solderless breadboard we bought, right? If we were to buy one off Amazon, it does not work. This one is brown, black, black. This is 10 ohms. So now we're going to have 10 times more current, or 500 milliamps, all right? Okay, now let's see what goes on here. Uh-oh. Look at that. 4.5. So we surely don't have 5 volts in our digital system. So if we had a analog digital, digital analog, if we had whatever, we're definitely not getting 5 volts. If we had a processor that we're running really hard, like a microcontroller that requires 5 volts for a certain clock rate, we're probably not going to be able to maintain that clock rate with that voltage. And as we're changing this load, this thing is not regulating at all, and that's got pretty hot because there's no regulator. Again, the solderless breadboard that we got off Amazon, if we got one of those, since this voltage is too low, it can't regulate. So at best, we're going to have whatever this voltage is as this changes. And we just saw it went from 5.08 all the way down to like 4.6 as we changed our load. And that's exactly what an electronic circuit does. A load's constantly changing, and this voltage is all over the place. Wow, no good, all right? So that's that. Now what I'm going to do is so all these power supplies basically do the same thing, okay? So now what I'm going to do is I'm going to plug in this cable and do a couple other quick things. So now I'm going to put it into a powered hub, which you can't see. All right, so I've got my powered hub. Now look at this. Now the powered hub is interesting. Over the same cable, now it's at 5.25 volts. So this is compensated for the voltage drop over the cable and given a higher voltage. Well, if you're looking for 5 volts, guess what? We just got 5.25 volts. And again, our regulator probably can't regulate, especially if it's a linear regulator and not an LDO regulator. 0.25 or 250 millivolts is still very hard. That's right at the edge of what a LDO is capable of. They need usually 0.3 volts or higher as the voltage to maintain regulation. But let's see how this acts. So maybe we could regulate that with an LDO. But let's go here. Let's just skip to the 100. There's 100. Uh-oh, we just lost regulation. So now at best, we're getting this voltage, and then let's go ahead and let's put this other load, this 10 ohm load, all right? And look at that, we're at a beautiful 4.5 volts. Okay, and then let me show you this. So now, that's with this one little cable, and then let's just say we had a longer cable, okay? So what I'm going to do is I'm going to get a 10-foot extension cable. So again, you might, have to, so here's a 10-foot extension cable, USB extension. Maybe you have to power something, from across the room, I don't know, but you put a long cable in and you don't really think about it. Wait a minute, this cable has got, 22 or 24 gauge wire. There's not a lot of conductivity in such a small piece of wire, so the resistance is fairly high at these high currents, and now things are going to get even worse. Okay, so now we're at 5.2. We were at 5.25 unloaded, right? Okay, so let's put our 100 ohm in there. Let's look at the damage done. So 100 ohm, we went down to 5.1. That's pretty ouchy. And remember last time we were down to like 4.5. What are we going to go down to now with our 10 ohm load? Oh, 4.3. Now we're nowhere near 5 volts. We are out of 5 volts. We cannot call that 5 volts. We're going to call that 4 volts at best, right? Okay, so the point is if you want to build a power supply that's going to be powered potentially off USB, you must consider the 5-volt USB line is not going to be 5, it'll be higher, it'll be lower, it won't be regulated, it won't be regulated well, the cable drops, so you have to have a buck boost converter on there. So that's number one design. On the 3.3, you can definitely get away with just a linear LDO regulator because the voltage is going to be usually around 4.5 to 5 volts, and you'll be okay with that. So that's one important thing. So number one thing I want you to take away, don't make assumptions, measure everything, test things. See, I got just 3 of these out here. If I was building a product, I'd have literally, well, I do have about 100 of these supplies, about 100 of them. I have about 20 different hubs. I have at least 100 different kinds of manufacturers of USB cables. So when I make a charging system for someone or a power supply for a company, I test all of this. So I don't play around. You have to test things and not make assumptions. All right, so I think, let's see, is there anything else here that I wanted to mess with? I'm trying to think, is there anything else? I just wanted to show you that. I think we're good. I think we're good. So let's jump back over to the computer and let's finish our work over there. All right? Okay, so we're back on the computer. The first thing let's do is let's go and take a look back at that power supply. So it's using this AMS 1117 regulator series. Okay, so let's go take a look at that. All right, so AMS 1117, and this is a great company, AMS. I use a lot of their parts, and if it is AMS, and let's just do a general search, AMS 11117, we'll just say regulator. Here we go, Advanced Monolithic Systems. All right, and here's the data sheet for it, for this AMS 1117 series. And if you can't find it on DigiKey, typically you can find it on Mouser, which, let's see, these are all Mouser. Let's crack open another Mouser here, and let's type in AMS 1117. And then also for those of you in other countries, a lot of times there's Element 14, Newark, and so this is not coming up here either. All right, so let's just go back to the data sheet that we found. All right, let me make this a little bit big so you guys can see it. All right, so what do we got? So 1 amp low dropout voltage regulator. Okay, so this AMS 117 is a low dropout or an LDO, and 5 volt to 3.3. So they've got all these different voltages, or it's adjustable. All right, now let's go look at what that dropout voltage is. All right, that's what we're concerned about. So we're going to go look at the 3.3 volts here, and 3.3 volts, and this is, well, this is saying if VN is 4.8 volts, here's what these voltages are. So 3.2, 3.3, 3.349. That's kind of showing you the variation there. And then here's the line regulation. So it's the line voltage changes. What are the percent changes is? percent changes, and then load regulation is as the load changes, how does that change too? So these are kind of the specifics of the regulator, but we're looking for this dropout voltage, all right? So you gotta parse through these data sheets. And again, if you're just jumping here and looking around, this probably looks like complete alien Klingon to you. However, you'll learn all this inside of the course. Here it is right here. So dropout voltage for all of these things is saying it is about, for any of these, for 1% and I out at 0.8. Okay, so they're basically saying if you're pulling like a lot of current out of here, you're going to need at least 1.1 volts, and 1.3 is the most you'll need. All right, so the bottom line is, for the 3.3 volt regulator to regulate, you need to have 3.3 plus 1.1, and at worst case 1.3. So 3.3 plus 1.3 is 4.3 is 4.6. You need 4.6 volts to maintain that so that things will work. So the 3.3 would actually work, but will the 5 volt work, right? Well, the 5 volt, 5 plus 1.3 is 6.3. The USB is nowhere near 6.3, so it won't work. So all of these designs are flawed. They're flawed when you have the USB plugged in, and it won't work. It will not regulate, and you will not have 5 volts. The 3.3 will probably work and probably be okay, but the 5 volt will not. Okay, so I just wanted to prove that to you. Now let's move on, and let's go back to our design. All right, so this is kind of the final product here. And so we're in Circuit Maker right here. Again, if you haven't taken the course, you don't know what Circuit Maker is yet, but this is the CAD tool that we're going to learn. Let's look at a couple features of this just from the graphical perspective. So ours has the barrel connector, so you can put a wall adapter in here. Then we've got a USB mini B connector, and I like these. These are much more hardy than the micro ones. The micro ones are just horrible. They strip after a while, and they're just no good. So I like sticking with this one right here. Everyone has those cables. We've got a on and off switch. We got a little LED here. Then we have switches here. We've got switches. So you can turn and switch from 3.3 to 5 volts, 3.3 to 5 volts, and then these go on each one of these rails. And then one thing you got to be careful of is the rails, the way that these are oriented on the solderless breadboard usually is it's plus, plus, minus, minus in this orientation. So whatever you do, you'll always have plus and minus, and if you look at one of these boards, and I'm going to get the orientation here correctly. Yeah, so if you look at one of these boards, from this side, as the numbers count 1 through whatever, typically that's the way you're going to put the board. You're going to, people count from the left to the right. So then we would put the power supply here. So if we put the power supply here, it looks like the bottom rail and the bottom rail are the plus rails, and that's exactly how this board is designed. The bottom rail and the bottom rail would be the pluses. Okay, now, and remember, I've actually had a student ask about this. This is just wire in here, right? You could put plus or minus here, you could put plus plus, you can do anything you want. These are just wires. So there's a wire in here connected all the way across that row, and then on the next row there's a wire connected all the way across the other one. So they're horizontally connected. Then here they're vertically connected, right? That's how those work. And again, you're going to learn all of that if you don't know that. Okay, so here's our 3.3 regulator. And this one is an LDO regulator. And you can see there's a lot of capacitors here. There's this FB1. This is a ferrite bead for filtering. And this is a low dropout. So this will work no matter what. Then here is our 5 volt regulator. Now this right here is a buck boost converter. So if the voltage goes higher or lower than 5 volts, it will maintain that 5 volt no matter what. So this is a little bit more advanced, and this is an inductor. And you can see there's a lot of components around here. These are mostly just for good design that I put in. Both of these can work with less components, but we want to make it very noise-free, a quiet power supply. It can tolerate voltage spikes and noise and all kinds of stuff. So that's what we're going to go look at in the design. And then let me turn this over. There's another feature here. So I threw on a couple of these terminal blocks, are called, and I put the grounds next to each other, and then here's 5 and here's 3.3. So say you don't want to plug this into anything, you just want to use this standalone, you could plug it in with the wall adapter or the USB connector, and then you can just run wires off here. All right, and then notice there's no mounting holes. I didn't want to make this thing any bigger, and I didn't just want to put random holes in here to kind of support it. I prefer to put rubber feet. So you could just stick rubber feet under here, under here, under here, under here, and this thing would sit up on top of the height of a solderless breadboard. Let's flip to the other side. All right, here we go. There we go. So there it is. The RAPTOR power supply eliminator, RAPTOR PSX power supply, Terminator, Eliminator X, Crash Course Electronics, PCB design. So this is a two-layer printed circuit board, and it's got top and bottom text. Normally that would cost a little bit more, but these days you can get the overlay on the top and bottom, and it doesn't cost anything, so I always put it now. All right, so that's it. And we're going to go back to this, but right now I want to go to the design. So we're going to switch here to this view here. All right, and I want to try and do this course and get this lecture within an hour and 15 minutes. So we got about another 20-30 minutes, and we're just going to drive right through this baby. All right, so let's just stay here, and we're not going to go anywhere, and we're going to do this. Okay, let's go to the design. All right, so we got the design here. All right, so the way I design everything is like in blocks, and that way I can reuse blocks. So what's cool is if I need another 3.3 power supply, boop, there it is. I just take it. I need another 5 volt, boop, I just take it, right? And so very object-oriented kind of electrical engineering design, and that's a good way to do things if the specification, features, and behavior of these particular power supplies meet your needs for whatever else it is that you're building. All right, let's start from over here. So here's the input. And so as I design this, we always have lots of parts that we can choose from, like the barrel connector, for example, right? So why did I pick this one? Well, typically I'm driven by cost, all right? So I'm driven by cost, performance, availability, ease of use, technical documentation. I have a number of these metrics that I use as I design things. Additionally, we need to make sure that the tool circuit maker has a library part in its library of this component. If it doesn't, that means I have to make it. So I'm trying to avoid doing a lot of work. And if I have a part that it doesn't have in circuit maker, if I can find another part that's similar, its footprint, its mechanical footprint is similar, then what I'll do is I'll use that part in circuit maker, but then I'll put a note and say, I really want to put this part here to myself, okay? All right, so this is the component right here. Shows some of the mechanical stuff, this and that. And then, if you look at the price, it's 87 cents, and at 100, it's 70 cents. I kind of design around the 100 and 1,000 point, usually when I'm pricing things out. That kind of gives me an idea. So it's a very cheap component, but it's not a $2 component. That's too much. And again, I've been doing this 30 years, 35 years, so I have a really good idea of how much things should cost, right? If they're cheap and reasonable. All right, so that's that part. And this is a 2.1 millimeter tip positive, barrel negative, and very common. And that's it. So that's what we're going to use. And it can withstand up to 5 amps. So we know we're good with whatever current. All right, then we come in here. And now this is going to come from a wall adapter, which could be either a regulated wall adapter, right? Or it could just be like a switching mode power supply like the Apple one, or it could be a real cheap one, like a big wall adapter. Let's grab one. So here is a wall adapter, and this is everyone's got about 100 of these. This is a 9 volt, I think. Yep, 9 volts at 500 milliamps. So what's in here? If you took the class, you already know there's just a transformer in here and a bridge rectifier and maybe a capacitor, probably a small one because they're cheap and they don't want to give us a good 2,000 or 4,700 microfarad capacitor to smooth out the ripples. So the voltage, 9 volts at 500 milliamperes, is not regulated. What that specification means, if you pull 500 milliamperes DC, you're going to drop the voltage to about 9 volts, but unloaded, that'll probably be 12 volts. And really loaded, it'll go down to like 6 volts. So the point is that 9 volts at 500 just means that 500 milliamps, it'll be about 9 volts. You can actually pull more current if you're willing to tolerate it dropping down to 6 volts, for example. Point is that voltage is going to be noisy and it's going to vary. So we're going to put a smoothing capacitor right here, a small one. I'd prefer to put a bigger one, but it's big and bulky, so we'll get away with a 220 microfarad. You could put 1,000 on there or 2,200, and you can actually find them in the same size. This one's 3.5 millimeter spacing between the leads, and this is a 6 to 10 millimeter diameter. This is just a generic capacitor. Just make sure it's got a big enough voltage, high enough voltage to tolerate whatever input voltage is times 2. make everything times 2 or times 3 or stuff will blow up. All right, so there's our input power. Now, here's our mini USB. This is another thing that people have trouble selecting, right? They're like, you know, there's 1,000 USB connectors. What should I do? Well, you gotta go look through them, and you gotta decide what you're doing. What are you building? This and that. How much money do you want to spend? So here you can see it's 54 cents for quantity 1, and a quantity 1,000, it's 32 cents. All right, and then this is what the connector looks like. What I like about it is you see it's got Kapton tape on it, that yellow tape, that's heat resistant tape. So this can be soldered on there with a reflow oven or hot air, and it'll survive. You can pull that tape off, so that's real nice. And then it's got those 4 mounts. So this is a surface mount device, right? And then we look at what can it tolerate for current. A lot of times it might have that. So current rated is 1 amp, cool. And mating cycles, how many times can I plug it in and out? 1,500, cool. All that's good. And that's a pretty cheap part. Again, if you don't know what you're doing, you'll just find some expensive part. You can find a $3 USB connector if you like, right? Bad. So anyway, again, that is a part that I like. I like this company EDAC, and Circuit Maker obviously had the component. So there it is. So we aren't using the USB as a USB. We're just using it as a power supply. So we have the positive comes here from B-bus, and then all these are grounds. Now, here's the ground, and then MTN 1, 2, 3, 4, those are the 4 mounting points. Bing, 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 and we want to ground all those as well. That's what's going on here. Now, what's all this, this AK? This is obviously a diode if you've taken the class, and this is a Schottky Diode. And what we want to do here is, if you've got this one in or this one in, I don't want one of these feeding the other one. I don't want one of them feeding the other one. So these diodes protect the current. The current can only flow from left to right, left to right. It can't go back inside of here. So for example, say if I plug both of these in and one of them had a higher voltage, it could possibly backfeed the other one, but not with these diodes. So this is called a wire or power connection. So current will only flow out, and then depending on the impedance of either one of these sources, one will be a source or one will not be a source. If you happen to plug them both in, no damage will occur. So you can plug either or whatever, and everything will be fine. So this is just, again, another diode, and very important, check this out. All right, let me blow your mind some more. And again, we got to compensate and think about all these things. So to make this power supply safe and robust for these different inputs, which the other guys didn't do, right? I don't think they did. But if they did, then here's another problem. Here's another problem we're going to have. Check this out. So we've got those diodes in front of that USB power, right? Okay, so this is a Schottky diode. All right, again, 36 cents at 1, and it's 6 cents at 3,000. I like it. All right, it can handle 2 amps. It can tolerate a 45 volt reverse voltage. That's all good. Forward voltage. Ooh, look at this. So at 2 amps, if you put 2 amps through here, 650 millivolts of drop is going to happen. So wait a minute. With the diode in the circuit, so we didn't even have a diode in that test we just did, a protection diode. We didn't have that. So you're telling me if I drag 2 amps, I'm going to lose 0.65 volts, maybe 0.3 volts if I drag 1 amp. So there goes another 250, 350, 450 millivolts of voltage I've lost. So there's no way I can regulate, because I've went from 5 point whatever down to 4.5. Now I'm down to 4.2 on that USB. So you see, it's all smoke and mirrors. It's fairy tales and unicorns. That power supply on Amazon, all of them don't work in the 5 volt mode. All right, unless you plug in a wall adapter and that's running at 6, 7, 8, 9 volts, then that linear regulator, that AMS 1117 5 volt, will have that 1.1 to 1.3 voltage it needs above the regulation voltage. But in USB mode, not going to happen. All right, so that's that part. Say, moving on, we've got a switch here. And so this switch is a Microswitch EG1271. And I like using small switches. I just wanted something small on here. If you go here again, and we'll go back in 3D mode. So I wanted something kind of fit here and fit here and fit here. Now, in the best world, I would want the switch to be able to handle more current. So these switches can handle 300 milliamperes per pole, I believe. So we're going to tie the both poles together. Oops. And now we're who knows where. You hit something on Windows, you know how that is. Let's go here. Okay. So in this case, we've got our circuit here, and we're just switching the power from the input here, either input, through the first switch into V sub CC in. Okay? All right. Once we've switched that in, then we've got a little power indicator here to let us know that power is on. We pick a 470 ohm resistor so that if it's being powered from the wall adapter over here, and maybe that voltage is higher, and maybe this voltage is lower, we don't burn out that LED. So 470 should be fine. So even if the input was 12 volts, so we take our calculator and we say, hey, if we had 12 volts as an input and a 470 current limiter, what's kind of our worst case scenario? It's 25 milliamps. That LED will be okay with 25 milliamps, and it won't even be 25 milliamps because the LED is going to drop a couple of volts, so it's going to be even less, maybe 20 milliamps. So that's okay. It'll be really bright in this mode. But anyway, you could play with that. All right, so let's back off a little bit. So now we've got our V sub C in here, and then here it is here, and here it is here. And now what we want to do is we want to put this into each one of these power supplies. All right, so let's start off with the linear one. All right, so again, there's a bazillion different kinds of linear regulators from all kinds of companies. And again, you got to pick what you like and your cost and what company you like working with. So I like working with Micrel parts, and Micrel was purchased by Microchip, I think last year. Anyway, so here it is right here, and here's all this tariff stuff, which is going on with a trade. So tariff applied, so that's good. All right, so anyway, one of them is $1.44 and 2,500 is $1. So it's $1, which is a good price. And again, you could have an input of up to 16 volts, so that's good. And then our dropout is 0.63 at 1 amp. So that means that you take 3.3 volts, add 0.63, about 4 volts. So that input better be 4 volts or higher, and we know it'll be with the USB. It'll definitely be like 4.2, 4.3. Or higher, even with that protection diode, and this thing can output 1 amp. So we're good to go. So we got an amp right there, all right, and that's the part that we're going to use. And sorry, this is, you know, Windows is, it never does what it's supposed to do. All right, there we go. Okay, so that's that, and then if we were to go, as a matter of fact, let's go back here. Let's go back to the data sheet here. Go back to the data sheet, and we'll just click that. They all have the same data sheet, and I believe I already have this one open. Yeah, here it is here. So what you would do is you get the data sheet, and you kind of look through here, and you kind of read, this is the one that we're going to use right here, and you look at what the minimum design is. Okay, so this is a very poor design. A lot of data sheets, honestly, are written by interns at companies, or they're the bare minimum so that the marketing department can say, hey, just with a 10 microfarad tantalum capacitor, this will work, right? Yeah, it may, but it's not going to work very well, and it's surely not going to protect noise and spikes and all kinds of stuff. This is a bare minimum. You need to do more than this, all right? You need to do more. All right, so in my design, power comes in here. We already know we've kind of smoothed things through this one with this capacitor here, but in this case there's nothing here. We're just going to take that power straight through here. Then we have this ferrite bead, which is going to filter high frequency noise. Then we've got a nice 22 microfarad and a 0.1 microfarad. Now this whole design is surface mount. These are all 0805 size, so those are what we're dealing with. And they're all generic. So say this 22 microfarad, whatever the voltage is, and you got to be careful of this, whatever the voltage is we anticipate, say on this power input, you got to be careful. So I'm going to just say put in 5 to 9 here. Actually, that should probably be, well, 5 to 9 would actually work, but not many wall warts are 5 volts, usually 6 to 9 or 12 volts. Anyway, if you put 12 here, that's kind of pushing it, 12 volts. And the reason why is if this capacitor is such a small component, the higher the voltage, the more expensive it is. So typically you can find 6.3 volts, you can find 10 volts, you can find 16 volt, 25 volt, 50 volt, and so forth. We really would like the voltage tolerance of this capacitor to be twice the input. So if we say from 5 to 9, so that's 9 volts, so it should be 18 volts. Is the worst case scenario this thing has to tolerate. So we'd like to pick something maybe 25 volt, right? So you got to be cognizant of that. Make sure these capacitors can take this input voltage from this input here, all right? And I usually double it, all right? So if you don't want to be that robust, it's going to go to 9 volts, But remember, it's a wall adapter, and it could float up to 12 volts or something. So if you say, oh, I'll just use the 10-volt capacitor, it'll probably work, but over time it will damage it, and then soon it will not work. So I always double it and then shoot for that. All right, so we've got a ferrite bead for high frequency noise, then we've got a couple input capacitors. This one's for smoothing, and this one's for noise. The 0.1's for noise. Then we have our regulator right here, and ground, and we have our output. Then again, another 22 microfarad. Now a 10 nanofarad, a very small one. Then we have another ferrite bead. Then we have another output capacitor here for noise. This creates what's called a pi filter, and again the class kind of talks about this, and it looks like the symbol pi right there and there, and this just really traps and filters high frequency, low frequency noise. So we just get DC out. Then there's a little thing here. This is a current sense resistor. So this is a very small resistor. In this case, I believe this one is 50 milliohms. So it's like there's no resistor there at all. But what this will allow you to do is put a probe on here. Let's take a look here. So right here, you can plug in like one of these little headers here, and then you can connect that to your meter, and you'll get a voltage will be generated over this tiny resistor. That voltage, of course, is proportional to the current flowing through here. So you can monitor the current coming out of each one of your power supplies right here at the source, which is a nice feature. So that's another feature our design has, is you can measure current, right? Okay. And let's go take a look at that current sense resistor real quick. Where to go? Right there. And again, I'm going fast as always, and that's one thing, you know, if you're taking the course, I kind of talk fast, but we have to. We just have a lot of material to cover, right? We're not making grilled cheese sandwiches. I've said that before, and there's just a lot of stuff to do. All right, so this is 60 cents for 1 or 8 cents for 5,000. It's 10 milliohms and 1% tolerance. So basically, this is like not even there, 10 milliohms. So it's like nothing. So this would be a tiny voltage generated here as the current varies from 0 to 1 amp. So at 1 amp times 10 milliohms is going to be 10 millivolts. So we need to be able to measure down to a tiny little voltage with our meter, so we need a meter that accurate, or you can use a larger sense resistor. You could even use 1 ohm if you want, or 0.1 ohm, right, to get a kind of a bigger voltage, right? And that's fine, all right. And then you can turn it back to a very small one, or you can even make it a short if you don't want this feature. All right. So that's it. That's the 3.3 power supply. Then we've just got a power good indicator. I always like to make sure my power supplies are on with instrumentation. I'll talk about that in the class. Put LEDs on things. It's like printfs and C code, right? Now, here's the bad boy. Here's the 5 volt. So we're going to talk about this in a second, but it's a very similar design. We have the voltage in. We've got a ferrite bead for filtering. Then we've got, now in this case, I've got these 10 microfarad. So what I'm doing here is I'm saying, hey, I want 20 microfarad, but I'm going to use 2 of these in parallel, right? So I can make these voltages really high, right? Because I want really high voltages. Now over here, this one right here, this one's 22. So, you know, why couldn't I have just used this one? Well, this 22 is kind of, you know, our suggestion. If we can find a 22 that'll tolerate, you know, maybe 15 volts of input, we'll put that there. But if we can't, we're going to have to drop that down to like a 10 microfarad at like 16 volts. But on this one, we can't. We definitely need more capacitance. So I put 2 placeholders, and let's start with 10 microfarad at like 16 volts. If we can find 22 at 16 volts, we'll put those in there, right? And make it like 44, 47 microfarad. But so that's what you'll see a lot. A lot of times when you see surface mount design, a lot of capacitors, they can't tolerate high voltages as these capacitors get smaller. So you'll see people put these things in parallel so they sum up so that you can get that bulk capacitance that you want. And there's our 0.1 for noise filtering. This has got an enable here. This is a little input that needs to have a capacitor connected to it. And then we're going to take a look at this data sheet. Then somehow we get an output over here. And again, 22, 22, 22. But now, wait a minute, the voltage on the output is 5 volts. So it should be 5 volts, and it should stay at 5 volts, so we can use a much smaller voltage on the output. I wouldn't use a 6.3, which is another common value. That doesn't make me feel safe, because if voltage ever fluctuates or spikes or somehow doesn't deregulates, or this thing is these capacitors over time lose their voltage tolerance and derate, you're going to hit that 5 volts, 6 volts, and these things are going to be damaged. So I prefer to put a 10 volt here. So 10 volts here, and I'd prefer to put like 16 volt here to make myself feel good when I sleep. All right, but anyway, again, I want to put them in parallel because I want that bulk capacitance, because this is a switching power supply, which we're going to take a look at, and it's got noise in it because it's switching. I think this switches at a megahertz, so we want to, really reduce the noise here, bulk capacitors, and then again, here's a small capacitor for filter, then here's a ferrite bead, going to filter high frequency noise. Another capacitor, we have different values here, creating that pi network. Again, we've got our current sense resistor port here, and then we've got our final V sub C out, and then we've got our power good indicator. We're going to swing back to this in 1 second. Now, how do we get the power out? Well, I just drew here's the 3.3, the 5 volt, and then we have a couple switches here, and then we run those switches to each one of these output rails. These are just those connectors, these things, right here, right here. That's all those are. All right, and we just connect those out there so that we can control each. And then there's those terminal blocks, right, which are these things right here, right? And that's it. So that is the power supply. So it's not that complicated. All right, so now let's go take a look at this actual part here. So again, there's so many of these switching regulators, and some are very complex and require a lot of external parts, which we don't like. We want to keep it simple. This one only requires an inductor. All right, it doesn't require a field effect transistor or a switch or any kind of craziness. So let's take a look at that. Actually, I think I have it, but let's go look at its cost. All right, so there it is. And with Texas Instruments TI, the TPS series has a lot of really cool regulators. TPS, isn't that from Office Space? TPS reports. If you are a fan of tech comedy, then you have seen Office Space, and you know what I'm talking about with TPS reports. If not, Google it. All right, so this is a little bit expensive. At quantity 1, you can see $277 and $250. It's $1.82. Switching regulators are not cheap because they're fairly complicated. All right, now let's take a look here. The maximum input is 12 volts, so we got to be careful. In the wall adapter mode, when we've got that wall adapter plugged in, if we do put over 12 volts, we're going to blow this thing up. So we definitely want to say only put a 9 volt wall adapter, and that's the max. All right, this is a 5 volt fixed output. Switch current is up to 2 amps, and this one switches at 2.4 megahertz. I said 1 megahertz, 2.4. All right, and again, we can go to the page. There it is. All right, you can see this right here. This package type. All right, which is called this WFD-FN exposed pad, or WSON, which I forgot the acronym. Bottom line is it's got this pad here for heatsink, and then these connect on it. So this is a fairly hard component to solder. You have to use hot air or reflow oven. You could solder this, maybe, if you're lucky. The way the pins wrap around, it's doable. I've done it before when I was much younger and I didn't have a hot air gun, 20 years ago. I've soldered these, but you want to have a hot air gun or a reflow oven to solder these kind of components. All right, let's take a look at the data sheet. Here it is here. It's a whole series. That's why there's an X here. Let's make this a little bit bigger. All right, so with these things, these are not simple. This is a 31-page data sheet. All right, and it's got some complicated stuff inside of it, some math in it and whatnot. All right, but at the end of the day, you could read all this, but at least just kind of skim through it. I've read hundreds of these, if not 1,000 of them in my lifetime. Probably over 1,000 actually, of different data sheets for these regulators, and made many power supplies. All right, so basically in a nutshell, here we go. So here's a simplified schematic. So the bottom line is V-in and enable are tied together here. We have a capacitor on the input, again, simplified, cheap, not really robust. That's why we have many capacitors. We need this Vaux through a capacitor to ground. This is this PS sync mode. This is power saving mode. This is the package ground, P ground. Here's this feedback. Here's the V out. And then again with the capacitor, and this is this power good. So, and this is with the, this is like an adjustable one that has a feedback loop. So it's kind of showing you that. And then you kind of go in here and read what all these pins do. All right. And then go down here and you kind of see the internal design of this. It's very complex. There's a feedback loop, and this thing adjusts and adapts. And I explain how buck and boost regulators work inside of the class, at least an introductory explanation of them. All right, then it kind of shows you what each pin does. All right, and then what we're looking for again is kind of these simplified designs. So here's like, this one's a 5-volt design here at 800 milliamps. So it needs this inductor, and then it's showing these components right here, and so forth. All right, so you kind of go through here and you figure out your design, and it says some suggestions for the components, right? Suggestions for the components, all right? Okay, so, and you can kind of read through. There's a lot of information in here, like I said. All right, so let's go back to the schematic. Okay, all right. So in this version of it, we basically read through that data sheet and we set this thing up like this. And this is how it's set up so that it's at a fixed 5-volt output for this particular part. And that's all we need to do. And then we already talked about that. So now we have our electrical design. All right, and we're doing pretty good here. We're doing pretty good. I think we can go about 10 more minutes or ish. All right, so we have our electrical design. So now we go to layout. All right, so now and there are many lectures on layout and so forth, so we're not going to go through too much of this. But the bottom line is, step one was I placed all these components down here, and you're going to learn this tool, Circuit Maker. I placed these components down here, and again, I explained what's my thought process. Well, first, this has to go here, and this has to go here, right? And then I measured and designed the circuit board in this shape so that everything would fit. And if we look at, say this distance right here, so we go right from the center here, right being there, and I just love the way things, so CAD tools, and I complain about it all the time in the course, these things are massive pieces of software and they're very broken, even the best expensive ones, which this is based on one of the biggest tools in the universe, Altium Designer. All right, so if you look down at the bottom of the screen, if I move the mouse, you're not going to be able to see it, but if you look down at the bottom of the screen, it says the delta is 47.59 millimeters, 47.5, and that's about what I measured when I measured it with a caliper. So I made it 47.5, all right? And then within the tolerance of the tool, that's how close I was able to get. And then from here to here is 0.1 inch, and then from here to here is 0.1 inch. So that I kind of get for free because the connector itself. All right, so anyway, these had to be placed exactly there. Then it's kind of like, the board's going to lay here. Then I said, maybe I'll let this little lip come over the board a little bit. Then I want to put these switches here, and I don't want the board to collide with the switches too much, and I want to have 3 of these so you can put it into the board really good. So I'll put the switches here. Again, we'll go back to 3D. There's the switches, and on the other side, these switches are going to be sticking out a little bit as we solder them through there. So if the board was here, we don't want it pushing on the board too much, so the board maybe is going to come to here, I think. All right, and then again, I do this in a block level design. So I pick where I want to put stuff. So I want to put the mechanicals here, and I kind of figure out where I want my mechanicals first. So I want the terminal blocks here. Here's the input switch. There's the USB connector. There's that big bulk capacitor, right? And then here's our 2.1 millimeter wall adapter port. So kind of here's all the mechanicals out of our way. There's our switches. There's our connectors for the Solderless Breadboard. Then I have to decide, let's put some electronics here. So I started with the 3.3 volt regulator, right? And then of course there's those 2 input diodes, right? And then you notice how these traces are thick. So all the power traces, there's a power trace, there's a power trace are thick, and then non-power traces are going to be thinner. Now, since this is a giant power supply, all the traces are thick. The only time you see a thin trace, here's a thin trace, that's an LED. So that's powering an LED, so I'll let that trace be thinner. But everything else, you're going to see fat traces because we're going to be pushing a lot of current. Now, we're going to talk about this in 1 second, but when we go to these surface mount chips, well, obviously I can't put this fat trace here. It would short all this out, right, this fat trace. So you got to bring it down. No way around it. Just sucks, but you got to do it, and then you kind of make it big as it goes back out, right? But when you go to the surface mount parts, you got to make things back small again, all right? Okay, so there's my 3.3 volt regulator. Now again, I always design things, I want to make them functional, I want to make them cosmetic, I want to make them attractive, and I want to make them logical. And I like to think of things, and I also like things to connect so that I have the least amount of connections to make, or the length of the connections are the smallest as I'm routing. And this is an entire art form, and it may take you years, or some people decades to get good at this, but it's definitely not something you're going to get good at quick. You're going to have to build boards. Like anything, you're going to have to do it to get good at it. All right. Anyway, you can see how I've got that ferrite bead coming in, then we've got these couple capacitors on top of each other, and look, straight to each other, straight to each other, straight to each other, straight to each other. And then you see this one goes here, and this one goes here. Very clean, but also very organized and very pretty. And then, you know, the question, I could have put all these capacitors maybe longer this way, but it's kind of like I'm trying to get these to cluster in a nice small space, and so I can keep these lines large, these traces large. Then over here, here's our inductor. We go look at the inductor here, right? And then the inductor is going to sit right on there. Again, you know, these traces are small. These pins are small, right? These surface mount pads, not much I can do. So then I bring this stuff out here, and then I kind of fan it out. You know, I fan it out, make it big, and there's my inductor, all right? And then we just basically follow the circuit from the schematic and just place all these parts, make it real pretty, right? And here's my capacitors. They're all nice and grounded. Then something that we're going to learn, or you're going to learn when you do the course in Section 8 on PCB design, we're going to talk about this many times, is we're going to talk about noise and EMI and things like that at a basic level, right? You know, it would be a whole year course, again, on just PCB design with, you know, beginner, intermediate, advanced, talking about lots of these things with lots of experiments and simulation and analysis. But rules of thumb, we do what's called via stitching. And these little holes right here are vias, and these punch through the board to connect the different layers of the board for thermal conductivity and also to make the grounds connect together. And again, if you don't know what that means, you'll learn about it. But you can see there's these holes, these vias, all the way around the perimeter of the board. All right, all the way around the perimeter, and then around the power supplies. So you can see they're just punched everywhere because I want the grounds around here, and I want these things to be thermally solid, and I want these grounds from both the top and the bottom to be connected. And let's take a look at the bottom plane here. So I'm going to go to single layer mode. So there's that layer, and there's our bottom layer. So we've only got a few traces on the bottom layer. Both layers are grounded, so we've got nice grounding, and then you can see these vias much better here. All right, and that's the board. And then again, you can see when I'm running these big power lines. Now normally we want these 45s whenever we take a turn. We want 45s on signals. So there's a signal, you know, kind of a signal, kind of put that 45. But on these big DC lines, these are slow moving lines, only when you get into, you know, many megahertz, hundreds of megahertz, gigahertz, does it really matter to put these 45s, right? So that's for your digital logic and all that. But for power, it's DC. You can go ahead and make these things all 90s, and they just look better when they're 90s, and it's a, you know, a power tree. So you can see kind of power tree, power tree. There's our power tree, power tree, power tree. All right, and then when we're trying to make all these connections here, we, you know, kind of put a little bit of a little turn on them, and just keep everything nice. And we want a nice fill everywhere. This is all ground filled, completely ground filled. Okay, so there's our board, right? And so let's go to the next step here. Let's go, and so we've got the board, and again, you know, you're going to learn this tool in painstaking detail. But let's go to design rule check. Let's go to reset error markers. Let's run the design rules. Okay, I'm going to run the design rule check. There it goes. And oh no, there's all kinds of stuff wrong. Well, let's see what's wrong. Let's just close this. And we look over here, and error 0, warning 0, rule violation 64. Those are rules set up by the PCB tool that I didn't feel like modifying, and they're all the rules are things like this. See, silk to solder mask clearance. This one here is minimum solder mask sliver gap. So all these things are okay for me. I don't care. They're just fine. And many of them are generated because this overlay, the text, is going on top of things. Like here. I don't care. It's just text. I don't care about it. Doing that, that's fine. Everything will be fine. And then some of the other ones are the spacing between here and here is less than 10 mils, and that's kind of the default that the tool's set at. It's probably at 8 mils or 6 mils. It's fine because I know it can tolerate 5. I could go into the tool and fix all of those things, but I still like it to kind of spit them out at me just to say, hey, look at all these things, and maybe there's something I want to change. But they're all warnings, and nothing's going to happen. Okay, so the board is good. So now we can generate the files. Okay, so let's take a look at a couple things that are important. And even though we're going to go over this a lot inside of the Section 8 and the entire sub-course on PCB design, I just want to show you this. So when you have the board, you have to make sure you have a board outline. When I drew this, I basically took lines and drew this thing and painstakingly did this. It's a pain. Then I selected all the lines. Then up here in board shape, I said define from selected objects. And that allowed me to make a board shape. But then at some point, I have to make an outline of the board. So what I did was there's a function here where, again, you can go up here and you can say create, let's see, where is it? Create primitives from board shape. I think that's it. Define from select. Yeah, create primitives from board shape. Create primitives from board shape. Is that the one I want? Let me see. Yeah. So create primitives from board shape. And again, Circuit Maker is not usually the tool that I use. I use another tool. This tool, I don't know everything about it. So some things I can't remember where they are. But these tools are very hard to remember because there's so much anyway. In any event, there's a step that you need to make. After you make a board and you have your PCB and all that, you want to use this function here that we just went through, and we want to create an outline. So basically we say, I want it 1 mil thick. Basically I want it 0 thick. It's just an outline so that the manufacturer knows how to cut the things, all right, cut the board away. And then where do you want to stuff it? You can put it in any of these things. So we say, I want to put it in the outline layer, this layer, that layer, whatever. So when I originally did this, I put it into like mechanical 4, I believe, and then you hit OK, and then it'll generate it. So if we go here and we look at mechanical 4, there's that outline. So when we generate our Gerber file, we need to make sure we copy this file and then put the word outline on it so that PCB manufacturers know that this is the outline. Now there's also this one here. This is another one, but this is one I just drew so I could see the thing better. But this one I'm not going to use because it's too thick. And when the PCB manufacturer decides to cut this, does he cut it on the right edge? Does he cut it on the left edge? Does he cut it on the center? I'm not sure, depending on the manufacturer. Probably should cut it in the center, but why chance it? So that's why I made this other one that's 1 mil thick. Whichever way he does this, 1 mil thick, worst case, it's going to be 1 mil off, and I can tolerate that, right? So anyway, again, you're going to hear a bunch about this when we do the PCB design part of the class. So just extra reiteration of that information. Okay, so there it is, and then we go here, and we go generate outputs. All right, let's save it, and it's going to save to the cloud. You see a little cloud there when we save things. Yeah, we've been messing with it and stuff, and a lot of times just opening the file and mucking with it causes this to happen, and you have to recommit it and resave it, which is very annoying. All right, and we're about an hour and 15 minutes, so we're good. All right, now what do we want here? Now you could have all these things, bill of materials, schematic print, blah, 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 blah. Don't care. All I want right now is I want the Gerber files, which are the manufacturing files. I want the drill files for the holes. The NC drill files are called, and NC stands for numerically controlled. And then I want, we don't need the pick and place because we're not having robots build this or whatever, but a lot of times I just like to generate that just for fun, but you don't have to, all right? So let's just turn that one off. And now let's go to the Gerber files and look at the configuration. And again, I go over this in detail in the course. So what layers do we want to output? The top overlay, the top paste, the top solder, the top layer, the bottom solder, all those. And then I output both of these outlines. And remember, this is the fat one. We don't really need that one, that GM3 layer. We don't need that layer. So you know what? Let's just turn that off like that. And we do need mechanical 4. All right, and then you can go through all these things, and I talk about all these things in inches, and this should be set for 2.5 and all that. All right. Anyway, so that's good. We go to the NC drill files. This doesn't have much. It's just inches, and it should be set for 2.5, and these should be the exact way you see them here, which we go over in painstaking detail in the course. And that's it. So we're ready to go. Now we say generate, and if we're lucky, it's going to say where to put this. So we're going to put this right here. And then we've got this manufacturing, and then this is the name of the file. I could change it to whatever I want, so I'm just going to save it here. All right, and then I'll close this. Okay, now we have our file here like this. So now what I'm going to do is I am going to extract all into a directory here. All right, and then of course you can find this file. I'm going to show you the name of it on Circuit Maker on their cloud, so you can just search for it. If you just search for my name, you can probably find it, but it's, Crash Course Electronics Power Supply version 001. We'll look at it in 1 second. It's literally this exact name right here. Crash Course Electronics _ Power Supply _ V1 _ 001. There's the Gerbers and there's the NC drill file. Now, let's go here and look at the Gerbers. Okay, there's that GM4, that's that outline, right? So what I like to do is this. I like to rename this here, just so there's no confusion. All right, boom. Okay, so there it is. So there is the Gerber file, okay, and then there's the NC drill file. Then what we can also do here is we can put this all in one zip, but we can also just take this this file right here, this text file, and if we want, we can just dump it into this Gerber file as well, right? Because this TXT file, it'll open up. So you can kind of do it either way. All right. So what we're going to do is we're going to just take this text file. I'm just going to copy this, all right? And as a matter of fact, we can do this. And there's lots of ways to do this. In the course, I do a couple of different ways. So there's no harm. Put these. The manufacturing people will look through this stuff and figure out what it is, okay? Or their automation will. So we're just going to put this all in this Gerber. I'm going to copy this here. I'm just going to paste this here. And some of these files are not used. This APR, this library, a lot of these are not used, but we're just going to keep them all in here. Okay, now we've got all our files. Let's move this over here out of my way. And I'm pushing into 1:30 here, an hour and 30 minutes total video time. After I edit, it'll probably be 1:15. So we've got to wrap this up. And let's get this tool here. So this is ViewMate. I'm going to talk about this in the course, but right now all I'm going to do is show you. So basically I'm dragging the files in here. Guess what? There's that top layer. That looks good, right? The top overlay. That looks good. Let's see. Top paste. There's the solder paste. That looks good. Bottom overlay. There's that RAPTOR PSX. It's backwards, of course. Bottom layer is that bottom layer. Looks good. And let's see, anything else fun? Top solder, that's the solder mask on top, and then we should have bottom solder. There's that. And then let's see if the NC drill file will do what it's supposed to do. There's the drill file, and then here's our outline file. And sure enough, so now we have everything we need to do the manufacturing. So let's come back here. So we have all these files. So all I'm going to do is I'm going to literally select all these things, and I'm just going to send these to a compressed file. And I'm not going to call it 001. I'm going to call it power supply. We're going to call it test. We're just going to call it power supply test zip so we can remember. So that's the file right there. All right. Now let's go build this thing. So we're going to go out here and we are going to go to, let's go to Osh Park. Here it is. Osh Park. All right, we're here at Osh Park. I'm already logged in. Good. All right, so let's get started. So it just says browse for files, or just drag. I think you just drag it here. So we're going to literally, this is pretty cool, literally drag the zip file, and if everything works, it should find everything and generate our project. And it did. Now, one thing that's very important, I teach in the course and I do in the printed circuit board design, is we're going to go over all kinds of manufacturing, how to look, how to go to different manufacturing companies and all that. So anyway, so we got everything's green light, looks good. We detected a 2-layer board. Here's its size. 3 boards will cost you $19.65. $19.65. All right, and then we can just go ahead and say continue, and you can see them right here. The rendering is really amazing. It's even lit correctly. I mean, it looks real. It looks like a photo. And then it shows you every single layer. So we can see that this is correct. This is what it's going to look like. There's our text in the back. That's fine. You know, Crash, the C in course is going to get a little jacked up, but I'm fine. You know, don't have to be completely perfect. This looks really, really pretty. Bottom solder mask, the board outline, bottom silk, top layer, top silk, bottom layer, etc. And then we just go to order. All right, we want PCBs, we want 3 of them. You could order more if you want. This right here, now I believe, let's see, does the price change if I do that? I don't think it does. anyway, I want 2-ounce copper, so I think this allows me to make it from 1 ounce to 2 ounce, and there's no additional cost. Whenever you're doing a power supply or anything like that, you want heavier copper, so 2 ounce I definitely want. This doesn't do anything, and I definitely don't want super swift service. And then you just hit checkout, put in your address, put in this and that. I mean, these things are literally 20 bucks, and then depending where you live, you can get whatever, right? And then again, we can go to board preview, and we can look at this again just to make sure we're ordering the thing that we think we're ordering. And that's it. So that's an entire process of the schematic design, the board, the reason we're making it, comparing it to the other product that we saw on Amazon, why those products are flawed because of their 5-volt supply, kind of going through everything, generating the Gerber files, reviewing them in ViewMate or a Gerber file reviewer, and then taking those files and sending them to a manufacturer and build it. Of course, you got to order the parts and build everything. Let me talk about 1 minute about that. In the design here, so again, this thing is called Crash Course Electronics. Here's the name, Crash Course Electronics Power Supply version 1001. So if you go onto Circuit Maker and you search for projects in my account, Andre Lamoth, Crash Course Electronics _ Power Supply _ V1 _ 001, you're going to find this thing, and then you can fork it. You can fork it and build it and change it and do whatever you want. All right. Let's go back here. All right. But one thing I want to bring your attention to is these parts. If you go and look at the actual part inside of here, right, the footprint is correct, but I'm telling you I want it 22 microfarad, right? And we talked about the voltage, but look, watch what happens if I click on this, and it'll go here. Look, it says it's a 47 microfarad, 6.3. Why is this different? Well, this is just the description of the generic part that I used for the footprint. Then I went and manually changed it. So when you go and get parts, you're going to get 805 size parts, but you're going to find each one of these yourself. All right, you're going to find a 0805 22, 085.1, etc. The only parts you know exactly what I want are the Macrel part. See the part, I put the part right there in these ferrite beads. All these capacitors and resistors, this is just generic. This I put the part number, I want you to use that one. This one I put the part number, I want you to use that one unless you want to change it. Look at the generic LED, it's just a generic 0805 and a 220 resistor. Everything's generic. These are very generic, right? These things right here, these headers, it's generic. This connector is pretty generic. The capacitor is generic. These terminal blocks, those are specific. Now, many of them will fit in the same thing. You could order a different, like here they are right here. But you could order different ones. They would probably fit in there. But anyway, use the part number I say, which is this one. So right here, it's this onshore technology, OSTT, whatever it is. And then these switches, I want you to use these EG1271. Again, these are micro switches and they're real small. So if you change the switch, it may not fit. Okay? But basically everything is generic except the chips, these ferrite beads, and this USB connector is very specific. You have to use this specific one. And then on the diodes here, you can use either this one or this one, if they have either one in stock. All right, that's when you build your bill of materials. Okay, so I think that's it, and my time's up, and that was a long lecture, about an hour and 15 minutes. So that is all there is to it. So definitely, if you're up to it, go on to a Circuit Maker Cloud, pull down this project, fork it, and take a look, see if I made any mistakes. I haven't built it. I actually sent it out for manufacturing, the PCB, but I haven't built one of it. And again, that's something I'd like you to do. Go ahead, build it, see if I made a mistake or whatever, but I think it's okay. And we went over to the design. But the whole idea is I just want to show you how you can take a look at a product that exists, improve it, find its flaws, and amazingly, tens of thousands of people, God, hundreds of thousands of people are probably using those solderless breadboards and they don't work. I guarantee they don't work. If you've got one, check that 5-volt supply. It's not working when you've got the USB port plugged in. Definitely not working. So you're all using broken supplies. And so you can just make something better and make a better version of it, and then of course sell it. So who knows, I might take this power supply and maybe add a couple things and manufacture it and sell it on my iConstructs website, right? And that's just another product. All right, so I think that's it. I hope everyone liked this bonus lecture, and I'll think of something else cool to do on the next bonus lecture. We probably won't do another design. This is kind of big. This took, in the background here, I took a few days to kind of put this together and get it all ready. So I'll think of something maybe a little bit simpler that's not as long. All right. Well, anyway, I will see you in the course. Bye for now.